Dielectrics and Gauss Law. Capacitor with a dielectric. What happens to a capacitor if you fill the space between the plates of the capacitor with an insulating material, such as material oil or plastic? Capacitance increase by a number of factor kappa called dielectric constant. C equals kappa C air. Remember, this formula is so important. It's the fact. Okay, the fact. Okay, the capacitance increase a number of K kappa called dielectric constant. Every dielectric material has a characteristic dielectric strength, which is the maximum value of the electric field that it can tolerate without breaking down. In a region completely filled by a dielectric, all electrostatic equations containing the permittivity constant epsilon zero are to be modified by replacing that constant by kappa epsilon zero. Electric field for a point charge inside a dielectric. E equal to 1 over 4 pi kappa epsilon 0 Q over R squared. We replace epsilon 0 by kappa epsilon 0. Electric field just outside an insulated conductor immersed in a dielectric. E equal to sigma over kappa epsilon 0. For unfixed distribution of charges, the effect of a dielectric is to weaken the electric field that would otherwise be present. Look at this circuit. A capacitor is connected with a battery. Okay, so it was charged. The V across the capacitor is equal to electromotive force, the battery, okay, and C equal to Q over V. This V is epsilon, okay. When you put a dielectric between the plates, we will find the charge increase. Why? Why? Because the fact C equal to kappa C air. This is a fact. The measurement result, you have to exceed it. Remember that one. C increase, so V is constant, so Q is increased in this case. Now, the constant V, the Q increases. We see that another situation. We just connected this one with a meter, okay? And originally it was charged to V, a same V like this one. And then we connect to a voltmeter with very huge internal resistance, right? Now we put the dielectric between them again, and we find the V across this capacitor decrease. Why? Because in this case, V changes. Something does not change, the charge. So in this case, the Q does not change, okay? But anyway, C changes by the fact. So C increases, V must decrease. That's the fact, okay? Constant Q, so V decrease. Different condition, we have a different result. That's physics, okay? Sample. A parallel plate capacitor whose capacitance C is 13.5 picofarad is charged by a battery to a potential difference V 12.5 volt between these plates. The charging battery is now disconnected and a porcelain slab kappa equal to 6.50 is slipped between the plates. What is the potential energy of the capacitive slab device, both before and after the slab is put into the place? We know the energy stored in the capacitor is half CV squared. Now, originally, before the slab is put into the place, this is C is 13.5. We have to use the Faraday as a unit, and the picum is 10 to the minus 15. Okay, and the volt, okay, this one. This is the answer before the slab is put into place. How about after that, we know that one. Okay. After the slab is put into place, the U final equal to half Q squared over C, replaced by kappa C. Okay, and you calculate, you get the answer. Someone might notice that the answer here is 5050, and when we use the calculation, we used 1.54.6. What happened? Because the significant number in this question is 3. So we get 3. You get 3, is we drop this one, we get 1050. But when you do the calculation, we put more number inside. You get 162 picojoule. So delta U equal to U final minus U initial. Okay. We get minus 893 picojoule. Negative. Why is negative? Because the capacitor would exert a tiny tug on the slab and would do works on it. We attract the slab. The slab was introduced with no restraint, and if there was no friction, the slab was oscillating back and forth between the plates.
This electroscope and a large parallel plate capacitor will be used to demonstrate how inserting a dielectric affects the voltage on a capacitor. We first charge the capacitor by touching it with this charged rubber rod. The electroscope deflects, showing the voltage on the capacitor. If we insert a thick piece of acrylic between the plates of the capacitor, what will happen to the deflection of the electroscope? The deflection decreases, showing a decrease in voltage. When we remove the dielectric, the voltage returns to its former value. A sheet of cardboard inserted between the plates shows a similar effect. This animation shows how the charges move between the electroscope and the capacitor as the dielectric plates are inserted. This parallel plate capacitor and an acrylic sheet will be used to demonstrate the force on a dielectric between the plates of a capacitor. The sheet is attached to the end of a balance arm so that it is free to swing up and down. We'll place it between the plates of the capacitor and charge the capacitor to a high voltage using this electrostatic generator. When the capacitor is charged, the force on the dielectric pulls it down between the plates. This animation shows how the polarized molecules of the dielectric are reoriented by the electric field of the plates. This new orientation results in an attractive force on the dielectric, which pulls it down between the plates.
Dielectrics, an atomic view. 1. Polar dielectrics. That material is molecular with a permanent electric dipole moment. Without external electric field, they arrange randomly, so there will be no electric field. When we apply an external electric field, and these dipoles were lined up with electric field. Okay. And you look at in the central part, you have positive, negative. Okay, positive, negative. You don't see any charge, extra charge. Only on two ends, you see the positive charge on this right and negative charges here. Okay, then you will have an extra induced electric field. 2. Nonpolar dielectrics. This material, the electrically neutral atoms, okay, they don't have dipole. Okay? And when we apply an external electric field, they induced electric dipole. And these electric dipole will line up with E, external. The positive charge is moved along the E direction. The negative charge move opposite the E direction. So you see, in the neutral part, central part, negative, positive, they are neutral, no extra charge. Only two ends. This end you have positive charge. This end you have negative charge. So they have this charge will produce an extra electric field E prime, opposite direction of E original. And the total E is the sum of these. And since they are in the opposite direction, so total E is smaller than E. Dielectrics and Gauss Law. We have learned this one. Gauss Law in vacuum. Okay. Epsilon phi equal to Q, and phi equal to E dot dA integration. Okay. How about the Gauss Law in dielectrics? So Gauss Law with dielectrics is very easy. You put kappa in front of E. Okay. Everything looks the same. All right. I will prove it in a special case. We replace epsilon 0 with kappa epsilon 0. And we move the kappa inside the integration. Okay. And more important is this Q. When we have a dielectric put in external force, we will have an induced charge on the surface. Okay. That makes things complicated. But here is a free charge. Okay, so that's very important, the free charge only. Now, next, I may prove this equation, this law, in a special case. The special case is parallel plate capacitor. I prove it, the equation. Okay. Now, this is a parallel plate in vacuum. We are quite familiar with this one. How we find E, we make a Gauss surface, which is a rectangular box, right? Yeah. And we prove this one, okay? We get epsilon E zero C equal to Q and E0 equal to Q over epsilon 0A. So that's what we have done yet. I'm not going to repeat it, okay? Now, with dielectric material between them, what happened? What happened on the surface of this dielectric material? They will have an induced charge opposite to the original charge. So this is positive, this is negative. This is negative, this is positive. Now, we want to find the E in the dielectric material. What we do, similar to this case, we make a Gauss surface as a box. Okay. The top surface is in the plate, where E equal to 0. Right? And the bottom surface, it passes through the point in concern. Okay? And by symmetry reason, the E on the bottom surface will be the same as the one I want to find. Right? And we have a 4 side surface. Okay, we know 4 surfaces has E dot dA equal to 0 because they perpendicular. Right? Now, similar to this one. First, we write the equation. The Q inside this Gaussian surface, the Q is different. Free charge plus induced charge. So actually they are different sign. So this Q minus Q prime. And similar to this one, we get the equation is E equal to Q minus Q0 over Q0A. Right? I'm not going to repeat it. Okay. And then what they do, we find, hey, this one by experiment equal to epsilon 0 over kappa is reduced by factor of kappa. Okay. What is epsilon 0? Now, we can find this without the dielectric material. It's Q over epsilon A. And we write this one, Q over epsilon A. Now, let's compare these two equations. Epsilon 0A, epsilon 0A. So Q minus Q prime equal to Q over kappa. And then we put this Q over kappa, replace this one. We get epsilon 0, E dot dA, this replaced by Q over kappa. And then we move kappa to the left and we'll come into the free. We get the one we want. This important equation, although derived for a parallel plate capacitor, is true generally and is the most general form in which Gauss law can be written. Note the following. 1. The flux integral now deals with kappa k. The vector epsilon 0 kappa k is sometimes called the electric displacement d, epsilon 0 kappa e, called electric displacement d, so that the equation can be written in the simplified d. Integration d dot dA equal to q, because this is a d, okay? This is another form of Gauss law in dielectrics. 2. The charge Q enclosed by the Gauss surface is now taken to be free charges only. Okay, we don't consider the induced charge. The induced surface charge is deliberately ignored on the right side of this equation, having been taken fully into account by introducing the dielectric constant kappa on the left side, has been considered this one. 3. Above equation differs from our original statement of Gauss law only in that epsilon 0 in the later equation has been replaced by kappa epsilon. Okay. We take kappa inside the integral to allow for case in which kappa is not constant over the entire Gaussian surface. Sample. Figure shows a parallel plate capacitor of plate area A and plate separation D. This is D. Okay. A potential difference V0, this is V0, is applied between the plates. The battery is then disconnected and a dielectric slab of thickness B is not total, and dielectric constant kappa is placed between the plates assumed as parallel. Okay. Assume A is 115 square centimeter, D is 1.25 centimeter, B is 0.780 centimeter, kappa equal to 2.61, and V0 originally voltage is 85.5 volt. Question A. What is the capacitance C0 before the dielectric slab is inserted? That's what you see by formula with the C0 equal to epsilon 0 A over D. And we put a number inside, we get the answer. Remember, all the numbers should be in standard units. A is square meter, D is meter, so we have to use this one, okay? And you get a C0 easily, okay? So 8.21 times 10 to the minus 12 farad. 8.21 picofarad. Question B. What free charge appears on the plates? Now, this is the question we just get it. Q equal to C0 V0 originally, okay? So we put them inside, we get Q0, okay, and V, and then we get, this is the free charge appear on the plate. Okay. 7.0 picking colon, because picking is 10 to the minus 12, so we get a 2 number. Question C. What is the electric field E0 in the gaps between the plates and the dielectric slab? This one, this E, between these two, okay, E. This E should be equal to this E by symmetry reason, okay? Now, same thing, we make Gauss surface like it before. We get the same answer, definitely, okay? This one in the space, free space, kappa equal to 1, okay? Kappa equal to 1. This is the Q. We get the same thing, very easy one, okay? So epsilon 0 equal to Q over epsilon A, the same thing as before. Now we put the number inside, we get an answer, E0. There should be unit, standard unit, okay? This is a 6,900 volt per meter, 6.9 kilovolt per meter. Question D. What is the electric field E1 in the dielectric slab? This one called E1. Then what we do, we have to make Gaussian surface passing through for them. For example, as in this point, okay? And we use this because of kappa inside. This is E1.8. This is the one we want to find. By the same reason, by symmetry reason, E as uniform, everywhere the same, okay? And EA is parallel to the DA, okay? And finally, we get this is equal to, look this one, okay? This is look good, okay? This is equal to minus Q. Why it's not included in this one? That's the advantage of our formula. This formula is only free charge. So we don't have to consider the induced charge here. So this is minus Q. Okay? And then we found the E1. By fact, we know E1 equal to epsilon 0 over kappa. Okay, you see the calculation. All right. We know E0, just calculate. Okay, we put them inside. We get the E1 inside, reduced from 6.9 to 2.6. Okay. Question E. What is the potential difference V between the plates after the slab has been inserted? In the process, when the slab is inserted, what does not change is the charge on the plate. Okay, that's the fact. Okay, this is what we have to notice. The charge does not change. The potential difference will change. Okay, will change. Okay, so the V whatever equal to E dot ds. Integration by definition from positive to negative. Okay, and E we have so E0, E1, E0. So this integration becomes 3. We allow lobes perpendicular to the plate from positive plate to the negative plate. We have 3 sections. Okay, the first one is E0, and this one is E0. The length is D minus B. And this one is E1B. So that's total answer. Okay, answer. So we put the number inside, we get the V. Okay. This is a elementary school math. I'm not going to do it. We just get you this answer. It's 52.3 volt. Question F. What is this capacitance with the slab in place? Okay, this should be, okay, C equal to Q over V. All right, we have a Q, we have a V, we put number inside. Remember, in this case, we cannot calculate C equal to C0 over copper. Why? Because it's not cover all the space. So we have to do it in this way. It's 13.4 picofarad.